Hi everybody, welcome to the third lab out of our 4 remote labs. This one is lab number 17, which is moment of inertia for our physics 180 class. I'm recording all of these in one night, so this is my third one. Let's see if I can keep with it. So, moment of inertia. Make sure you look at the document and your lab book for detailed instructions. But I hope to provide some context and show you the equations we're going to use during this lab. So we saw 2 labs ago, we worked with torque. And we saw that torque rotates an object. If we apply torque to an object, it rotates. And we related it to force in a lot of ways. It looked a lot like a force being applied. So if we think further about forces and we think about Newton's laws, force equals mass times acceleration, we might wonder if there's a similar law for torques. Is there a way that relates the torque to the acceleration? Certainly there is, and that equation's the main one from today, is that torque is equal to I times alpha. So this is a torque. Let's go. Torque is equal to the angular acceleration times this new quantity we're going to deal with today, which is the moment of inertia, which we just call I. You might wonder what the units are on the moment of inertia. Units for a moment of inertia are kilograms times meters squared. We can find that from the equation. Torque is Newton meters divided by acceleration, angular acceleration, which is equal to 1. The units on angular acceleration are 1 over second squared. Remember, angulars don't have, they're in radians, which aren't a unit. So torque is Newton meters. Angular acceleration is 1 over seconds. We know newtons are kilograms meters per second squared. So we get kilograms meters per second squared times meters times second squared, to move this to the other side. So the second squareds cancel out, and we get kilograms meters squared per a moment of inertia. So we see moment of inertia depends on the mass, which we would expect because it's related to this equation, where it's mass times acceleration. But this mass is weighted somehow by the distance of the masses. So moment of inertia is kind of a weighted mass. It tells us something about how the mass is distributed. The basic formula for discrete particles for moment of inertia is I equals the sum of mass times radius squared. So maybe you have a bunch of different particles rotating around an axis. It depends on each of these masses, the masses of each of these particles, and the distance they are from the axis. R1, R2, R3. So we can sum these all together to find the moment of inertia. The classic example that everyone has to talk about if you're talking about moment of inertia is a figure skater. Figure skaters are masters at moment of inertia. You're going to see this figure skater is pushing off the ice, going into a spin, and she's not going to push herself again. Just from controlling her moment of inertia, controlling how her weight is distributed, she's going to be able to change how fast she's spinning. So after that initial push, you see she starts out pretty slow, with her mass widely distributed, a big R² value. And as she brings that mass in, she's going to speed up. She's not pushing herself anymore. She's just spinning up by controlling that moment of inertia. You don't have to be a pro figure skater to do this. You can be this guy. He's on an office chair here. He's going to give himself a push, and then you can see him speed up and slow down by just moving the masses inward. It's really weird. If you got a spinning chair at home, try it at home. Grab your water bottle, grab anything heavy, your physics textbook, and give yourself a spin and try it out. So what these two examples are doing is they're the same mass. They're not adding any mass, but they're decreasing the radius of that mass. So by decreasing the radius of the mass, and it's squared, so it matters a lot, the moment of inertia is decreasing. And if we look at our TIA equation, if the moment of inertia decreases, and they provided the same torque, they only pushed off once, so it's the same force, the angular acceleration has to go up. So torque constant, mass constant. If inertia goes down, then acceleration goes up. So torque, mass are constant in these examples. I said a couple. Torque was only last time. Oh, I said torque was 2 times ago. It was only 1 time ago. But momentum's the easiest equation in physics, mass times velocity. Torque, I think, is the easiest one to remember. This torque equals I times A is just the last 3 letters of inertia. Great way to remember this equation. Tau equals I times alpha is TIA, the inertia. Okay, but moving on from a discrete, we don't really have particles around an axis. We have a continuous distribution. So if we do a real object, not just a particle anymore, the moment of inertia is the integral, the mass integral of R² dm. Alright, so we don't have to do integrals in physics lab, but I thought I would do this one real fast. Let's do this integral for a disk. That's what we're going to be dealing with today. A solid cylinder spun about the middle. Anytime you see a mass integral, you can change it to a volume integral by using density. I is equal to rho, which is the density from 0 to r of R² dV. So you're changing that mass integral into a volume integral. This is the same equation. This one we can work with for a disk. We know density is equal to mass divided by volume. The volume of a disk, of a cylinder, is the area of a circle times the height. So the volume is pi r squared times the height. And if we do dv dr, we get 2 pi r h. We can move that dr to the other side, and we now have our dv. So we've got our rho, and we've got our dv that we can plug in here. Just the area of a circle times the height, and taking the radial derivative. So we get I is equal to the mass of the disk divided by pi r squared h times the integral from 0 to the radius of the disk of r squared times 2 pi r h dr. 2 pi r h dr. So we can combine those r's. So this is now r to the third. We can pull out the pi h, and it's really weird that the pi and the height cancel out. That the moment of inertia of a disk actually doesn't matter how high the disk is, how thick the disk is. So now we've got r to the third. If we take the integral of that from 0 to r, that would be I equals, oh, this is the total volume out here. So this should be big R2. So this is big M over big R squared times big R to the fourth times 2 over 4. So that's our 1/4 being pulled out by doing the integral. And the 0 cancels out. So just big R. And sure enough, that gives us that I is equal to 1/2 mass times the radius squared. So you can do these integrals for all kinds of different shapes, or most people have just tabulated them. You can look up on Wikipedia. I should do this real fast. Wikipedia moment of inertia. And if you do this, there's a gigantic list of all kinds of shapes somewhere down here. Did they move it? Rigid body. Oh, it's not on this page. There is a page where all of these things are tabulated on Wikipedia. They have a huge table of all kinds of different moments of inertia. But we're going to be dealing with this one today. This is one of my favorite, this 1/12. It's kind of a weird number that pops out of a thin rod. But we're going to be dealing with the cylinder today. Our apparatus looks like this, that you won't actually be using at home, but you got the data for. We're going to be spinning this disk and actually experimentally determining its moment of inertia. So our properties here is this disk has a radius of big R. And we've also given you the big mass of the disk. We're going to measure its moment of inertia by spinning it by dropping a mass to the ground. So we're going to put some certain amount of mass on here. and drop it to the ground and measure the time it takes to go the height. This is attached to a string that's wound around a hub in the middle. There's a hub in the middle here, where the string is round around, and the radius of that hub we're going to call little r. So this is a pretty specific setup, but it's going to allow us to calculate some pretty cool things. So the equations we need today is we're going to start out by measuring the acceleration of the mass. By dropping it to the ground, we see that it's just free fall. So it's 2x over time squared, where x is the height that the mass is going to drop. We've given you a bunch of different data of different masses and how long it took for those masses to reach the ground. From this acceleration, we can calculate two things. We can calculate the angular acceleration. The angular acceleration is acceleration divided by radius of the hub, small r. Anytime we move from circular motion to regular motion, or from regular motion to circular motion, we divide by r or multiply by r. So we see a is equal to r alpha, v is equal to r omega, and x is equal to r theta. This is moving from circular coordinates to regular coordinates, and we're moving back in this equation. So this is one major equation. You're going to be doing this more in class. And then from this setup, we can also look at the forces being applied. We have gravity pulling down. We have the wheel doing circular motion, slowing it down. And from these two, we have this acceleration happening. We can calculate the tension in the string is equal to mass times gravity minus that acceleration we calculated. So here's the mass hanging off times gravity minus that acceleration we calculated. And from the tension, we can get torque. We saw before that torque is equal to force times the lever arm, which in this case, the tension is at force, and the lever arm is that small hub radius. Sorry, torque is equal to tension times R, where tension is this value. I'm going pretty fast over these equations, but they're really specific to this setup. These aren't the big ideas here. Now if we put these two together, we got torque and we got alpha. We've got that original equation there, TIA equation. So we can see torque is equal to I times alpha. So what kind of equation is this? It's a linear equation. We've got 2 weeks off of linear regressions, so the next 2 weeks got linear regressions. If we do a bunch of different masses, so we get a bunch of different torques and a bunch of different accelerations, we treat these as x values and these as the y values, and we do a linear regression, and the slope will be our experimental I value, where our theoretical I value will be this one. the 1/2 times the mass of the disk times the big radius of the disk squared. But you see it's not a perfect disk, so it might be a little bit different. We're going to calculate that. The y-intercept should be close to 0. We're going to record the y-intercept as tau f, the frictional torque. There might be some friction applied, and that's going to be the y-intercept. So when you see torque tau f on your lab, that's the y-intercept of the linear regression. All right, linear regression. You're going to be graphing this one and calculating I experimental. It's pretty fast. This is really important though, and it's really important to me because moment of inertia is super important to understanding planet formation. You'll notice in our solar system, all the planets are pretty flat. They're all on the same plane. And we think that's because it formed in a protoplanetary disk. And we've actually seen protoplanetary disks. And this is a very active realm of research at UNLV. One of the grad students was very instrumental in analyzing all of these protoplanetary disks. And this is a big conservation of angular momentum problem. Think about it that you have a ice skater that's 1 light year across and super diffuse. And as that ice skater collapses, or that cloud collapses, that mass is drawn inward. And even if this, which is 1 light year across, had just a tiny, tiny bit of rotation, just a tiny rotation, as that collapses down into the size of our solar system, which this is only 100 AU, astronomical units. I won't go into all that, but much, much smaller, several orders of magnitude smaller. As it collapses down, that tiny rotation becomes a huge rotation, becomes super fast to Keplerian speeds, and it heats up the disk. So all this dust is heated up into a protoplanetary disk, and as it cools, it forms our planets. So this is what I study, and a bunch of astronomers study at UNLV. That's it for moment of inertia. Let me know if you have any questions. It's going to be a lot of plugging and chugging this lab, but the post-lab questions are pretty interesting this time. So good luck.